Okay, all right, Stuart. Galen has a special hello to you. We'll start off today. Galen,
Hello, Stuart.
that's all you get is a hello. Okay. We and Luke has a question. What, Luke? Oh, you have a question for Stuart. Okay.
Yeah, I was wondering if you could switch work for me and work for me on Friday so I can work on Thursday.
Ooh, need to switch work with Luke Ellis. I would leave Luke stranded. Text him if you can. Okay. All right, let's give this a shot. Calculus notes 3.5. Just like we have polynomials that we can take derivatives of, we can also take the derivatives of trigonometric functions. I think I mentioned back a while to you guys this fact that you can take sine of x and you can write it as a polynomial. And so on and so forth. That's calculus 2 where we learn how to do that. The point is that if sine was written in this form, it would be much easier to take the derivative of. And that is a form of mathematics where we learn that any type of function can be expressed as a polynomial. That is true. And so then you could take the derivative of any function technically, which is a pretty powerful thing to be able to do. However, we don't need to go through all that work. We could simply say this, and I think you guys will like it. Identify the derivatives of the following functions. The derivative of sine of x is cosine. That's not too bad, right? Yeah, I'm sorry. So new notation, d over dx, that means the derivative with respect to x. The derivative with respect to x. So sine changes with respect to x at a rate of cosine of x. That's kind of interesting. We'll graph it on the calculator later on. We'll see what it looks like. But cosine of x, the derivative of cosine of x is negative sine of x. And I gave you guys a sheet not too long ago that had a summary of a lot of stuff that we've learned so far. And that should be something that you probably keep on hand. It would be able to have this information for you as well. The derivative of tangent is kind of interesting. If you remember, tangent can be expressed in terms of sine and cosine. Do you remember how? Tangent is equal to sine over cosine. So if you wanted to be able to take the derivative of tangent, if you happen to know the derivative of cosine and sine, what would you do? You would use the quotient rule. So we're not going to do that. We just know it's secant squared. But since you guys had a very thorough understanding of trigonometry last year and you were experts at it, as you received a great amount of college credit for it, we would hope that with a little bit of practice, we could show that the derivative of a tangent by using the quotient rule is that. So we would hope that we could reduce an identity to work that through. The derivative of cosecant is derivative of cosecant is negative cosecant x cotangent x. And again, does anybody know what cosecant can be expressed as in terms of sine and cosine? 1 over sine. So that, right. That's a little bit trickier to find the derivative of. Derivative of secant is equal to secant of x times the tangent of x. And finally, cotangent of x, if we take the derivative of that, we get negative cosecant squared of x. I never forget the top three. I do forget the bottom three. When I haven't taught for a while, it's like, I don't remember exactly what it was. But the top three generally are pretty easy for people to remember. It'll be very helpful for you if you at least remember the first two, hopefully the third as well. And you can kind of work your way through there. Any questions on those derivatives? You don't know how we got them. You can look in your book to see how they are derived. I could show you before after school. But let's try some of the problems. F of x equals negative 4x plus tangent of x. I need to take the derivative. So that would be f prime of x is equal to, you tell me. Very good. That's it. How about the next one? We have 3 sine of x plus 4 cosine of x. What will we get? This is the common mistake that people made. Why do I put a negative sign? Because the derivative of cosine is negative sine. Nope, those are multipliers, just like if you had, let's say we had f of x is equal to 5x to the third. You would multiply that 3 by the 5 to get, so f prime of x would be 15x squared. So the 5 remains there. And so also the 3 and the 4 remain there. That's a good question. Any other questions? Okay, take out your graphic calculators before we do the rest of these. I want to give you a little bit of understanding of why sine and cosine are derivatives. Okay, so we have sine of x and we have cosine of x. Please type those in, and then we're going to change our window. Shh. We're going to change our window accordingly, and we're going to try to view these and get a good idea what they look like. What's that? You don't have to be in radians for this, but it might be a good idea for you at some point to adjust your window if you want it so that you are in radians. If you notice, you do have a zoom trig fit that works out in these situations. You don't have to worry about radians. Oh, I'm sorry. Okay, you guys, I totally forgot. I'm sorry. I lost my mind there. Luke was asking, do we have to be in radians? I thought he meant, do we want the scale on our x and y axis to be represented as radians? We don't need that. But you were asking, should we be in radians here? Yes. Yes, yes, yes. Mode. Okay, let's examine this. What I'm going to do is I'm going to bold sine. And then please change your window with me so that matches up with what I have, okay? Go to window. Let's make our x minimum, let's make it negative 2 pi. So negative 2 second pi. If you remember, sine and cosine repeat their values every 2 pi. So every 360 degrees, which in radians is 2 pi. If I ask you guys what is 30 degrees in radians, do you know? Pi over 6. And if I ask you what is 135 degrees, you cheaters, I gave you a sheet. Do you guys all see it? Morgan, show everybody what you're looking at. On the bottom of that sheet. Okay. Okay. Tammy Frondel, she graduated last year, 2 years ago. I think last year, I can't remember, but nobody knows Tammy. Tammy was FFA. Okay, all right. So Tammy was in my trig class. Yeah. Okay, so we have negative 2 pi. We have positive 2 pi. We'll have our scale be every If you want to, you can put your scalar every, say, pi over 2. So that shows tick marks every pi over 2 if you want. We'll go pi. Sure, you could do over 4. You could do over 185. So we have that. Our y minimum, what's the maximum value that sine achieves? 1. So I'm going to put my y minimum, I'm going to bring it to a negative 2. So I make sure I see the whole graph, and positive 2. So is everybody's graph where you want it? For the x scale, I made it pi over 2. X scale was pi over 2. Okay, let's understand graphically what's going on here, okay? I'm going to point to the sine function. You tell me what you think is approximately the derivative at that point. This is my sine function right here. At 0, what would you approximate that derivative to be? 1. And if you look at cosine, cosine has a value of 1 right there. So you can see that cosine is in fact the derivative. If you point to this value right here, what's the derivative of sine right there? And if you notice, cosine crosses right there. The derivative of sine right here be negative 1. And if you notice, cosine goes down to negative 1. So you can see that they do in fact show the derivative of one another. It just happens to be that the derivative of cosine would be negative sine, and you can make that relationship understood. So does everybody understand graphically why that happens? Sure. So right here, if you look at the derivative of this graph right here, it looks like the derivative would be about negative 1. And in fact, cosine has a value of negative 1 at that x value. So you can see that cosine maps all of the derivative values of sine over that given interval. And then it will repeat itself. Okay, so you see that. Let's continue on finding derivatives. Let's get to some harder ones. Those were boring. F prime of x equals 3x plus x cotangent of x. Well, this might be slightly more difficult. Does anybody recognize why? You need the product rule. Bryce, why do you need the product rule? X times the cotangent of x. First, I could take the derivative of 3x, which is 3. Now I need to perform the product rule. The product rule says the derivative of the first function, I have x and cotangent of x, so I'm going to work with x here. What's the derivative of x? 1 times, nope, times cotangent left alone, plus the first function left alone, which is x, times the derivative of cotangent. What's the derivative of cotangent? Negative cosecant squared of x. A derivative of 3x would just be 3. We don't have to work with that within the product rule. We're just going to work with this one right here and this one right here. Okay. So if I want to simplify this, I could just write it as 3 plus the cotangent of x minus x cosecant squared of x. Any questions? Do you have a question? Okay, so derivative of x, which was 1, this left alone, plus the derivative, or I'm sorry, this left alone times the derivative of that. So there we got it. There it's good. Everybody good? Okay, let's look at an example that looks significantly more difficult, but this is actually pretty easy, okay? Sometimes your knowledge of trigonometry really helps you out. And so I'm going to rewrite this function. I'm going to rewrite it as f of x is equal to, I have 2 over the cosine of x. It looks like I would have to use the quotient rule or something like that. But I don't need to, because 2 over the cosine of x is the same as what? 2 secant. These, Bryce, go ahead and say it. Yep, 1 over cosine is the same as secant, so therefore 2 over cosine is the same as 2 secant. So now we'll take the derivative of it. This is much easier to take the derivative of than that one, correct? So we'll try that. F prime of x is equal to, what's the derivative? 2 secant? 2 secant of x tangent of x. What's the derivative of 3? 0. So we have our derivative. Any questions on D? Okay, now we get to one that does pose a little bit more difficulty, and it's going to force you to recognize some trigonometric relationships. So if I asked a question on the test, one that was more difficult, this would be the question that I would ask. So this would be kind of the content limit for which I would expect you to be able to understand. You'll have one problem like this on your assignment. And this does require us to use which rule? The quotient rule. But before you use the quotient rule, you should first look to see, does anything simplify? Does anything reduce? And in this situation, nothing does. But if it did, hopefully you would recognize that relationship and see it. What's going to happen is after we apply the quotient rule here, you are going to see your trigonometric identities at work. This could simplify very well. So we'll write this. I wrote a new screen so I would have more room. F prime of x is equal to, you guys don't have anything on the backside, so if you want to do it there too, you sure could. But I need to take the derivative of what? The top times the bottom left alone minus the derivative of the bottom times the top left alone, all over the bottom squared. So we have the quotient rule up on the board in a few places, and obviously you have it in your notes. So let's put that to rest here. What's the derivative of the top? Very good. Times the bottom left alone. So I have x plus cosine of x minus 1 minus sine of x. So I'm taking the derivative of the bottom, which is 1 minus sine of x, because the derivative of cosine of x is negative sine of x, times 1 plus sine of x. All over x plus cosine of x, that quantity squared. Beautiful. Looks like the denominator is pretty set. Unless we get an x plus cosine of x up in top that we could cancel out, bottom is set. We need to be able to reduce the top. Let's start foiling here a little bit. F prime of x is equal to, we'll have x times cosine of x Sean's question is, could we factor out an x plus a cosine of x out of the top so it cancels out with the bottom? If there was another one over here, then yes. But this expression is one term, and this expression is a separate term, so you would have to be able to take it out of both. Does that answer that question? Okay, let's continue on. We plus, what's cosine times cosine? Cosine squared. Minus, now let's think about this. 1 minus sine of x times 1 plus sine of x. Those are conjugates. So what do you get? 1 minus sine squared. These are conjugates, meaning you have a minus and you have a plus. Otherwise, the expressions are the same, so you get 1 minus sine squared. So minus 1 and plus sine squared when you distribute the negative through. Should I write that again? Minus 1 minus sine squared. So I minus 1 and I plus sine squared. Okay? All over x plus cosine of x quantity squared. Super duper. What crosses off? Nothing. Not yet. We have to recognize a relationship. There's a key relationship up here. Cosine squared plus sine squared is 1. So look, if you take cosine squared plus sine squared, do you remember that relationship from trigonometry? On your sheets, let's see. Let's see, which one? This one right here. This one's beautiful. This one's this is a great sheet here. I have all the trigonometric formulas that I think are most valuable written on this one. And I think it says sine squared plus cosine squared is 1, right? That's the most important one to remember other than the relationships between, say, sine, cosine, and tangent. So if you look here, cosine squared plus sine squared is 1. So what you end up having is this. F prime of x is x cosine of x plus 1 minus 1 all over x plus cosine of x quantity squared. You like my x? So I recognize that that adds to 1. I now have 1 plus negative 1, which is 0. So my final derivative is x cosine of x all over x plus cosine x quantity squared. So that wasn't too bad, but that would be the content limit of one that I would ask you to be able to do. Maybe extra credit. Any questions on that? Okay, we got 2 examples left. What? I just did E. So there you go. He can hear us say everything, so he's all good. All right. Oh gosh, they're all watching me. Hi, yes, great to see you. It's Marlene and Chrissy, the entire school. Okay. How about this? You try to see if what rule are you going to use on the second one here? The product rule. Shh. Don't distribute first, okay? Don't distribute first. Okay, don't distribute first. Let's just simply let's use the product rule here and simplify. It does the theta make it different? The theta might as well just be an x. So see if you can solve using the distributive property there. Or I'm sorry, see if you can solve using the product rule there. I'll put Stuart, I'm going to put you on hold. We'll get back when I actually do the problem. Okay, let's pick up. Let's see where you guys got. I'm going to change the variable to x just because that's what everybody's used to working with. It doesn't really matter. It doesn't really change things. But I take the derivative of the first one. Again, I have 2 functions. This would be 1, and this would be 2. What's the derivative of secant? So I have secant of x times tangent of x times the second one left alone, which is x plus tangent of x, plus the derivative of x plus tangent of x. What's the derivative of x? 1. 1 plus secant squared of x times this part left alone, which is secant of x. Now, this doesn't reduce to anything really nice, okay? But we can write it just a little bit more simplified. For example, we would have x secant of x tangent of x plus secant of x tangent squared plus secant of x plus secant third. Not much you can do. Dunskies. Yep. Let's pick up with this bottom one tomorrow. Let's start practicing some of these problems. Okay, we'll pick up the bottom one tomorrow. Taylor, say bye, Stuart. Bye, Stuart. Later.